This is problem 1376. It's on page 726. Two mass streams of different ideal gases are mixed in a steady flow chamber while receiving energy by heat transfer from the surroundings. The mixing process takes place at constant pressure with no work and negligible changes in kinetic and potential energies. Assume the gases have constant specific heats. A. Determine the expression for the final temperature of the mixture in terms of the rate of heat transfer to the mixing chamber and the mass flow rates, specific heats, and temperatures of the three mass streams. You know, instead of reading it all the way through, I'm going to go ahead and start writing some of this down because there's a lot here. It's a pretty simple setup. We've got a mixing chamber with two gases flowing into that chamber. So there they are coming in. They mix together and they leave at stream 3. Now there's heat transfer. As these are mixing, there's heat transfer that comes in from the outside and adds to the energy in it. Now, one thing they mentioned is that the pressures are the same throughout the entire system. It's just an open system, so it makes sense that the pressures would all be equal. And we're supposed to neglect all kinetic energy and potential energy changes and assume that there's no work interaction, just heat interactions here. Now, what they're asking us to find for part A is the temperature at the exit right here, T3, as a function of, so that's what I'm going to write here, the heat transfer rate in, as well as the mass flow rates. Let's see, what did they say? Of the three mass streams. So we can use the mass flow rate of stream 1, stream 2, and stream 3. We can also use the, specific heats. So CP1, CP2, and CP3. Notice I'm using the constant pressure heat capacity because when fluid comes in, it's going to have both thermal energy and it will have flow energy. So I need both. So CP will take care of both. That will give me a relationship to enthalpy essentially. But then also, this will be functions of the temperature at stream 1 and stream 2. Of course, it can't be, function of T3. That wouldn't make any sense. So that's the first thing we're supposed to find. For B, they ask us to obtain an expression for the exit volume flow rate in terms of the overall rate, in terms of the rate of heat transfer to the mixing chamber. So let's jot this down. Volume flow rate at the exit in terms of, Q dot N, fine. What else? The mixture pressure. Let's see. The universal gas constant, specific heats and molar masses, or in other words, molecular weights of inlet and exit. So the gas constant RU and specific heats CP1, CP2, and CP3. And then finally, the molecular weight 1, 2, and 3, also called the molar masses, which is a better name really than molecular weight. I'm just used to molecular weight. So for part C, when there is adiabatic mixing, in other words, when there is no heat transfer in, for that special case, then they want us to find or show that the exit volume flow rate, V dot 3, is a function of the two inlet volume flow rates, V dot 1, V dot 2, and what else? And the specific heats and molar masses of the inlets and exits. So specific heats, CP1, CP2, CP3, and M1, M2, M3. Should be a comma in there. There we go. Now one thing I want to note about this that's important is that the state 3 is a mixture state. So anytime you see 3 here, we're talking about the mixture of 1 and 2. And then finally for part D, we're supposed to show that if both gases are the same gas 1 equals gas 2 if you will, if they're the same thing, then we just need to show that the volume flow rate, and of course Q dot N equals 0. I think they said that, adiabatic mixing and the same ideal gas, then show that V dot 3 is simply V dot 1 plus V dot 2. So we've got our work cut out for us. It's not too difficult a problem, but a lot of students don't like this sort of problem because it just seems theoretical and therefore pointless. But the point here is to show how things relate to one another. And so these properties are not completely independent. There are things going on that depend on one another, and that's the whole idea behind what we do here. So I'm going to bring to bear an energy balance first of all, because I think that that's the way to go. Notice we've got heat capacities and temperatures. That makes me think of Cp times T, which makes me think of enthalpy. And of course, you know, I've got to include this energy somehow. What's the best way to do it? Well, I think an energy balance. So the mass flow rate in stream 1 times its enthalpy plus the mass flow rate in stream 2 times its enthalpy plus Q dot N had better be equal to the mass flow rate in stream 3 times the enthalpy in state 3, the exit. Now I need to do something with this because I don't really want to use enthalpies. I'd like to use CPT because that's what I've got available to me. So if you think about it, changes in enthalpy can be approximated as Cp delta T. Now we don't have a change in temperature yet or change in enthalpy, but maybe we could. What if we use our reference state to be enthalpy equals 0 at, looks like a heart, not an at, there we go, at a temperature of 0. In other words, an absolute temperature scale, okay? So if our reference state is that the enthalpy is defined to be 0 when the temperature is an absolute 0 Kelvin, make that clear, that's probably a better way to say it. Well then, this difference would become the enthalpy in any state minus the enthalpy in the reference state equals Cp times the temperature in that same state, let's say H1 for example, T1, minus the temperature in the reference state, which is just 0. Now if the enthalpy is 0 at a temperature of 0, then what we're left with is this idea that we can write enthalpies as CPT as long as that temperature is the absolute temperature and everything should be okay. So that's what I'm going to use to replace the enthalpies in this equation. So I'm going to write the mass flow rate in state 1, Cp T1, plus mass flow rate state 2, Cp, and I've got to be careful here because it's stream 1, stream 2, so they have different heat capacities. And then let's see, T2 plus Q dot N equals M dot 3. I don't want H3, I want, CP3 T3. And so now I can write the temperature in state 3 as the mass flow rate in stream 1 times the heat capacity in stream 1, temperature in state 1, plus mass flow rate state 2, Cp2 T2, divided by M dot 3, getting ahead of myself, Cp3. So there's the expression they wanted me to write. It's in terms of the mass flow rates, the heat transfer rate, and the heat capacities and temperatures of the two incoming streams. As long as the temperatures are in absolute units, we should be okay. So let's just make a note. T absolute in this whole problem, or in this whole problem. Okay? So that takes care of A. How about B? Well, B is asking about the volume flow rate. So what can we do? It looks like we need to somehow get rid of the mass flow rates and include the pressure in our equation. Now, since we're dealing with an ideal gas, that makes me think of using the ideal gas law. So let's see what we can do with this. First of all, how would we write the volume flow rate in state 3? Well, let's do it here. Let's see, is that the best place? You know what? Let's not start there. Let's start over here, I suppose. The volume flow rate in state 3 could be written as the mass flow rate in state 3, which I know we don't have it yet, but we're going to end up using this, I think. Well, why else would we have written it? But let's just discover and see what we can come up with. The specific volume in state 3, if I multiply this out, this should work, right? Because this is the mass flow rate, so the units are, what are we in? Well, we don't know if we're metric or English. It doesn't matter. I'll just go metric. This would be kilograms per second, for example. And the specific volume would be cubic meters per kilogram. So we get cubic meters per second, which is a valid volume flow rate. So this should work. All I need to do is somehow express the specific volume in state 3 in terms of whatever I can use, the gas constant, the pressure, and so forth. And that gives me the idea that, well, let's just use the ideal gas law. So since this is an ideal gas, V3, well, let's see, it'd be P3 equals R, let's see, T3, right? So PV equals RT. Notice I didn't write the universal gas constant here yet, as they want me to, because I'm using the mass specific volume, not the molar, not per unit mole, right? I'm using it per unit mass, per kilogram. So this is not the universal gas constant yet, but I could solve for the volume in state 3 pretty easily as RT3 over P3. So we're a little closer. We've got the pressure, and I don't really need the 3 as a subscript because the pressure is the same everywhere. But I do need the temperature in state 3. By the way, I have an expression for the temperature in state 3. So I can write that the volume flow rate in state 3 is the mass flow rate in state 3, R over P. Let me just put all that together. And then times T3, but T3 is M dot 1, CP1, T1, plus M dot 2. And you know what? I made a mistake. When I was solving this, I made this same mistake. I was copying these terms and I completely forgot Q dot N. I apologize. Q dot N should be in here as well. And it would just be right there. Okay. So I just forgot to write it down. So it'd be all of these things on the top divided by the factor on T3. So there we go. So anyway, corrected that mistake, which is good. Plus Q dot N, all divided by M dot 3 CP3. Okay. So now we have an expression for the volume flow rate in state 3. What do we need to get rid of? Well, we need to get rid of all the mass flow rates. So the first one I see that can go easily is M dot 3. Let's just cancel it out. Why not? But we also need molecular weights. The gas constant, I think we could get into here. We could work that in pretty easily, but let's not do that quite yet. Why don't we go ahead and just multiply through? And let me show you why. Because look, we've got a gas constant R, and I need to be careful here. I'm sorry. This is the gas constant on the exit, so this is R3. So I should have a 3 on that. Making a lot of mistakes as I go, but that should be the gas constant for 3, because the properties of state 3 depend on the mixture coming in. So it's the mixture gas constant, or the apparent gas constant of the mixture. Anyway, the mass flow rate in 3 still cancels, but I see something here that looks familiar. It looks like, see, we've got an MRT over P. I'm beginning to see this and think, well, wait a second, that kind of looks like an ideal gas law. So I'm going to go ahead and just multiply this through and we'll see what happens. So let me jump down to here and say V dot 3 is equal to, let's see, we'll pull that through. So I'm going to try to make it look like the ideal gas law the best that I can. Let me pull out the heat capacities first because they don't belong in the ideal gas law. So CP1 over CP3 for the first term. And then I'd have M dot 1 R3 T1 over P. Okay. Now the pressure is the same at state 1, 2, and 3, so why don't I just go ahead and say this is P1 in this case. And that's just this first term here. The next term, I'm going to do the same thing. So let's see, plus, we're going to have CP2 over CP3, can't forget the denominator. And then M dot 2 multiplied by R3 T2 over P. But this P, it could be P1 if I want it to be, it could just be P. I think I'll make it P2. So you see I'm trying to make this look like the ideal gas law for a particular state. So that takes care of this term. The last term, of course, I can't really do a whole lot with at this point. I just have to multiply things out. So R3 Q dot N over, since this has R3 and I've got CP3 here, I think I'll go ahead and make this P3. Not that it has to be. Again, they're all the same, so it doesn't really matter, but I'll just write it that way. I don't think that one will end up mattering. These will. I have a reason for writing these this way. My reason is that I'd like to somehow invoke the ideal gas law. So continuing, we have CP1 over CP3. And looking at this, I'm really close to the ideal gas law if that was just R1. Well, I can make it R1. I'll multiply by R1 over R1 and leave R1 out here and an R1 in there. So this really looks like the ideal gas law for state 1. We've got an M, it's an M dot, it's not a mass, but it's a mass flow rate, RT over P. Let's do the same thing here, so plus CP2, CP3. What I need is R2, so I'll write R3 over R2, M dot 2, R2, T2 over P2. Okay, so now that looks a lot like the ideal gas law for state 2. And I guess I'll just leave the last term alone. R3 over P3 Q dot N divided by CP3. Now, as a quick aside, the ideal gas law that says PV equals MRT could be written as sort of a rate thing. In other words, if there was a mass flow rate, it would be a volume flow rate that would be related to it. Okay? We've seen this before, so I won't prove that to you. But this does work. We can talk about a volume flow rate related to a mass flow rate for an ideal gas in this way. And so if we rearrange this and say, well, the volume flow rate equals M dot RT over P, you can see why I've arranged this the way I have. M dot RT over P is just the volume flow rate. So this whole thing here is nothing more than the volume flow rate coming in at state 1. And this is nothing more than the volume flow rate coming in at state 2. So what I've done here in one fell swoop is I've gotten rid of the mass flow rates in favor of the volume flow rates, which I needed anyway. The only thing I have left to do, I'm sorry, I pointed the wrong thing. The only thing I have left to do is get rid of, let's see, actually it looks like I've jumped ahead a little bit because I was supposed to write the volume flow rate in these terms, but I've got V dot 1 and V dot 2. Let's see, I must have lost myself in my notes. So let's see, I think I skipped ahead. There's 1, 2. Yeah, I don't think I could actually do this because I need the mass flow rate somewhere. Maybe I misread the problem statement. Let me double check that. That was part 2. Obtain an expression for the exit volume flow rate in terms of the rate of heat transfer to the mixing chamber. That's Q dot N. That's okay. The mixture pressure, universal gas constant, and the specific heats and molar masses of the inlet gases and exit mixture. I don't think you can really do this because you have to know something about the mass flow rates. And so is there any way to get rid of them completely? I don't think so. We know this is true because this is just an energy balance, but that doesn't relate to V dot 3. This does. But let's see, this would not quite get me there because it has temperature in it, and I'm not supposed to have temperature according to this. Let's see. So if I plug in this for temperature, I end up with mass flow rates from here. See, so the temperature in state 3 is dependent on the mass flow rates of 1 and 2. And of course the heat capacities and properties of those things. So I don't think this one's actually possible, so I don't think we'll be able to do that. Although I can write it with a volume flow rate, so I think I basically can do this, but with the volume flow rates instead. So I'm going to have volume flow rates here also, V dot 1 and V dot 2. And then I'll take the special case where Qn is 0, but for now, I'm going to allow myself to have v dot 1 and v dot 2 because otherwise I don't think there's any way to write this. So part B is technically not really possible. Did I miss anything? Let me read it again. Obtain an expression for the exit volume flow rate in terms of the rate of heat transfer to the mixing chamber, the mixture pressure, the universal gas constant, and the specific heats in molar masses of the inlet gases and exit mixture. Yeah, I think they just forgot to say that the volume flow rate can depend on the incoming volume flow rates, because there's going to be no way to get rid of these volume flow rates. I mean, how would we get a rate out of this without that unit of time in the denominator? So that'll be fine. We'll just include v dot 1, v dot 2 in our specification here. Now, we weren't supposed to have the gas constants as we have them, you see, the R over R, or even this R, for example. So how can we rewrite those? Well, what is a mass-based gas constant? It's simply the universal gas constant divided by the molecular weight. So this is where the molecular weights will come into the picture. And so if I want to write R3 over R1, for example, then all I really need to do, well, let's see, R3 is simply RU divided by M, and it would be M3. R1 is RU divided by M1. So you see how the RU's cancel. If we then invert and multiply, then this is the same thing as M1 over M3. So I can just remember this pattern. R3 over R1 is M1 over M3. And I can make the substitution. So I'm just going to take this, instead of writing R, I'm going to write M, and I'm just going to flip the subscripts, because I know that it'll come out right if I do that, see. So CP1, CP3, can't do anything with that, but that's okay because I'm allowed to have those. And then this would be M1 by M3, V dot 1 for this term, plus CP2 over CP3. I can do the same thing here, but here it would be M2 over M3, like what I did here. And then V dot 2. Now, this gas constant I can get rid of by writing R sub U over M3, and then I'll have P3 CP3 also in the denominator in Q dot N. So here's the best I can do. Maybe I'm missing something. I really don't think so, because otherwise, without some flow rate, you can't have time units here. So I think the problem's just a misprint. So what else? Well, that takes care of B, now that I can do it, since I've allowed myself those volume flow rates. It is in terms of pressure. I guess I can get rid of this 3 because it's just the pressure. And I've used the heat capacities as they've asked, so I think we're good to go. How about when Qn is 0? Basically, the only difference with part C versus part B is that there's no heat transfer, it's adiabatic. And all that really means is that this term goes away. So V dot 3 would be CP1 over CP3, M1 over M3, V dot 1, plus then CP2 over CP3, M2 over M3, V dot 2. So there's the answer to C. We're allowed to use the volume flow rates I have, the heat capacities, and the molecular weights. So that's what I've done. Finally, we're supposed to show that when gas 1 and 2 are the same, then the volume flow rate at the exit is simply the sum of the two entering volume flow rates. That's actually pretty easy to see, because if gas 1 and 2 are the same gas, say just nitrogen flowing in, for example, then gas 3 is simply going to be nitrogen also. So all of the properties, the molecular weights would be the same for 1 and 2 and 3, because 3 is just a mixture of 1 and 2. The heat capacities would be the same, and so in that case, basically CP1 equals CP2 equals CP3, and M1 equals M2 equals M3. That just proves then that V dot 3, pardon me, is V dot, what order do I have in? 1, V dot 1 plus V dot 2. So from here, if these molecular weights are all the same, the heat capacities are all the same, well then the exiting volumetric flow rate is just the sum of the two entering volume flow rates. Again, assuming that there's no heat transfer in, so assuming that it is adiabatic. So we were able to accomplish the goals and write the various things, the temperatures and so forth, the volume flow rates in terms of other properties, the inlet properties essentially. So we're just basically simulating nature, right? We're just doing what nature would do, and nature would determine these properties by simply mixing the gases together, and the mixed gas would have whatever heat capacity, CP3, as the result. Okay. Interestingly enough, there's some other things you can do here that I haven't mentioned. Notice that the mass flow rate in state 3 is equal to the mass flow rate in state 1 plus the mass flow rate in state 2. That's just a mass balance. Okay. It doesn't matter how much heat you add, this is going to be true at steady state. So we could have used that, and along the way had an expression for m dot 3 in terms of m dot 1 and 2, but it was unnecessary. And I think probably the biggest trick here is just realizing that you can write the enthalpy as CPT, where the temperature is the absolute temperature. Let's see, was there anything else they asked us to do? No, I think that was it.